Hi, this is episode 3 of the Quantum Rings Quantum Summer School. Today, we're going to be talking about entanglement, which is a really bizarre phenomena that lies at the heart of quantum computing and allows us to perform powerful computations. Entanglement is really counterintuitive, so today is all about getting a feel for it and developing an intuition. Today, we're going to start by understanding entanglement in the context of 2 qubits, and then we'll move on to more than 2 qubits. And in the second half, we're going to talk about quantum teleportation. We're going to teleport a quantum state. Let's do it. Last week, we talked about single qubits, and today we're going to talk about 2 or more qubits. The first thing we need to talk about is how do we express a 2-qubit state. So if you'll recall, we can think about our state as living on the surface of the Bloch sphere, where 0 is the North Pole, 1 is the South Pole, and all the equal superposition states live on the equator. So in the case of 2 qubits, we can think about what are all the possible measurement outcomes? Well, one situation we could have is that the first qubit is in the 0 state and the second qubit is in the 0 state. Another possibility is that we could measure the first qubit to be in the 0 state and the second qubit to be in the 1 state. We could also measure the first qubit to be in the 1 state and the second qubit to be in the 0 state. And the last possibility is that they're both in the 1 state. So there are only 4 possible measurement outcomes. And we can express this in ket notation as follows. So we'll have the possibility of measuring 0, 0, the possibility of measuring 0, 1, 1, 0, and 1, 1. And just like before, for instance, the probability of measuring 0, 0 is magnitude of alpha squared. And the probability of measuring 0, 1 is the magnitude of beta squared, and so forth. So our normalization condition in the 2-qubit case is that alpha squared plus beta squared plus gamma squared plus delta squared needs to be equal to 1. We can also write this down in vector notation. So in this case, we would have alpha, beta, gamma, delta, and this here would represent where this first element is the 0, 0 state contribution, the second element is 0, 1, the third element is 1, 0, and the last element is 1, 1. So let's talk about where this comes from. We're talking about 2 qubits that are unentangled. So how do we describe 2 qubits? Let's say we have one, psi 1, which is alpha 1, 0, plus beta 1, 1, and another state, psi 2, which is alpha 2, 0, plus beta 2, 1. How do we construct that 4-component vector? Well, what we're going to do is called a tensor product. So the total state is going to be psi 1 tensored with psi 2. And what that looks like is as follows. So we'll have like alpha 1, beta 1, tensored with alpha 2, beta 2, and we just take the first element here and we multiply it by both elements of the second one, and then we take the second element of the first one and multiply it by both elements of the second one. So that's how we construct our 4-element vectors. We can do a quick example. So if qubit 1 was in the 0 state and qubit 2 was in the plus state, we would have the following: 1, 0 tensored with 1 over root 2, 1 over root 2. And this would give us 1 over root 2, 1 over root 2, 0, 0. And we could also write this down as 1 over root 2, 0, 0, plus 1 over root 2, 0, 1. What about the state 1 over root 2, 0, 0, plus 1 over root 2, 1, 1? So let's say we want to express it as a tensor product. So we have our alpha 1, beta 1 tensored with alpha 2, beta 2. And this is going to give us 1, 0, 0, 1. actually with a factor of 1 over root 2 out front. So what does this tell us? This tells us that here, both alpha 1 and alpha 2 need to be non-zero. And this last element here tells us that both beta 1 and beta 2 need to be non-zero. But then what's happening here? Because these are zeros, that means that something here has to be 0, so that they multiply to 0. So this tells us that this state, 1 over root 2, 0, 0, plus 1 over root 2, 1, 1, cannot be expressed as a tensor product. And this is the signature of entanglement. So a state is entangled if it cannot be written as a tensor product of the separate qubits. And another thing is that when you measure one qubit, you also collapse the state of the other qubit. So in the case of 0, 0 plus 1, 1, if I have one qubit and I measure it and I get 0, then that wave function has collapsed, and now we're simply in the state 0, 0. So if I measure the other qubit, I know with 100% certainty that I'm also going to measure 0. Just to write that out more explicitly, if we have the state 1 over root 2, 0, 0, plus 1 over root 2, 1, 1, and we have our state psi. This is how we normally draw quantum circuits. We can apply a measurement to one of the qubits. And let's say the measurement outcome from this is 1. Then when we measure the other qubit later, we're also going to get 1. Another really bizarre thing about entanglement is that this wave function collapse happens instantaneously. And this should raise some alarm bells maybe, because as you probably know, nothing can travel faster than the speed of light. So isn't there something going on that's from one qubit to the other qubit that's telling it, oh, the wave function has collapsed? This turns out not to be the case. So if we have two characters, our good friends Alice and Bob, and they have an entangled pair of qubits, which are in this state 0, 0 plus 1, 1. And then Alice stays on Earth, and Bob goes all the way to Mars. And they each take their qubit with them. Now, light takes about 12 minutes to travel from Earth to Mars. So let's say Alice measures her qubit, and then 1 minute later, Bob measures his qubit, and then they come back together on Earth, and they share their measurement results. They're always going to be in agreement. Just think about that for a second, because it's very bizarre. And Einstein referred to this as spooky action at a distance. The important thing to note here is that no information actually moved faster than the speed of light, because Alice and Bob only compared their answers later, so they didn't actually learn anything. Now I want to talk about creating entangled states. So in order to do this, we need a gate called the C0 gate, or controlled NOT gate. And it looks like this. It has ones on the diagonal in the upper left, but then the X gate in the lower right. And the action of the C0 gate is to flip the target qubit when the control qubit is in the state 1. So, for instance, if we have an arbitrary state psi equals alpha 0 plus beta 1, and we have our control qubit being 0, so this here indicates the control, and this here indicates an X gate, then our final state in the end would be alpha 0 plus beta 1. Nothing happens. On the other hand, if we have the control qubit being in the 1 state, then we'll end up with alpha 1 plus beta 0. So now let's consider adding in superposition into the mix. So let's take our first qubit and apply a Hadamard gate. So after this point in the circuit, this qubit will be in the plus state, and the second qubit will be in the 0 state. And we know that this looks like 1 over 2, 0, 0, plus 1 over 2, 1, 0. Then we can consider what happens after we apply a C0 gate. So in the cat 0, 0, nothing happens, but in the cat 1, 0, we're going to get a bit flip on the second qubit. So our final state at the end is 1 over 2, 0, 0, plus 1 over 2, 1, 1. And this is a maximally entangled state. So there's 4 maximally entangled 2-qubit states, and these form a basis for all 2-qubit states. So they're phi plus and minus and psi plus and minus is what we're going to call them. And they differ in some ways. So one thing is that the parity of the qubits can either be even or odd. So for the even ones, either both qubits are 0 or both qubits are 1. That would be even parity. An example of odd parity is when they're different from each other. And then we could either have no phase on our state, or we could have a phase difference between the two cats. So now let's move to the coding notebook and practice with all of this. If you don't see episode 3 in your Quantum Summer School repo, then go over here where it says Git, and then up here to the cloud symbol with the down arrow, pull the latest changes, and then when you go back here, it should appear. Another thing, make sure you choose quantum rings for your kernel. First, let's import the libraries that we need. And then today we talked about creating entanglement. So we know how to create the Bell state phi plus, which is 0, 0 plus 1, 1. And we can do this by first applying a Hadamard gate and then a C0 gate. So let's make the state phi plus. And one thing I want to point out here is the ordering of bits. So in this case, Q0 is the least significant bit and Q1 is the most significant bit. So when we see the state in ket notation, Q1 is going to appear first and Q0 is going to appear second. So here we have our qubit 1. We're going to apply a Hadamard gate, and then we're going to apply a controlled X controlled on qubit 1 targeting qubit 0. And then we'll get the following state vector, which is root 2 over 2, which is 1 over root 2, 0, 0, plus 1 over root 2, 1, 1. So how should we modify our circuit to make phi minus? Well, we need a phase on the second ket here. So we should use our phase flip gate, which is a Z gate. So let's apply a Z gate on qubit 0. And then when we output the state vector, now we have the state we want, 0, 0, minus 1, 1. Now, how should we modify our circuit to make psi plus? We want 0, 1 plus 1, 0. That means that our state has odd parity, so we need a bit flip. So let's apply a bit flip gate, the X gate, to qubit 0. Okay, what about psi minus? So now we need odd parity and a phase. So let's think about how to do this. We want a phase on this second state here, second ket. And so we have to think carefully about the order in which we apply things. So we can first flip the phase of the second state and then apply an X gate on Q0, which is the second bit here. Okay, and then there's some quiz questions here if you want to check your understanding. So what if I gave you a Bell state and I told you measure these two qubits exactly once and tell me which Bell state it is. Could you do it? Think about this for a second. Well, if we just measure both qubits, we can learn the parity of the state. So if you measure both qubits and they're both the same, you have even parity. And if you measure both qubits and they're different, then you have odd parity. So you know if it's phi plus or minus or psi plus or minus. But you can't tell the difference between phi plus and phi minus or psi plus and psi minus. So last week, we saw that you can tell the difference between plus and minus in one shot if you apply a Hadamard gate right before you measure. This Hadamard maps the plus state to 0 and the minus state to 1. So we rotated from the z basis into the x basis. So think about this for a second. This is a hint, and think about how you might apply a similar idea in order to rotate us into the Bell basis. So first, we have a helper function to prepare Bell state. We just provide the name of the state, so phi plus or minus or psi plus or minus, and then which qubit is the target and which qubit is the control. So here we're going to prepare the Bell state phi plus, and then we're going to perform our Bell state measurement. So we're going to apply a controlled x, controlled on 1 and targeting 0, and then we're going to apply a Hadamard gate on qubit 1. So let's see. So we measured 1,024 times, and we measured 0, 0 every time. So now the question is, what result do you get for the other 3 Bell states? Try this on your own first. Okay, so let's look at it. If we prepare the state phi minus, then we measure 1, 0. If we prepare the state psi plus, we get 0, 1. And if we prepare the state psi minus, we get 1, 1. So a follow-up question is, can you say anything about the relationship between the measurement result and the parity and phase of the Bell state? So one thing that we can notice is, for instance, for both of the states psi, we have a 1 as a second bit. So every time we're in an odd parity state, the second bit is going to be 1. And then every time we're in a state which has a phase, the first bit is going to be 1. So now let's talk about GHZ states. This is a generalization of the phi plus Bell state. So it's a maximally entangled state which takes this form. So we have one state which is all zeros plus one state that's all ones. And just a quick note on notation. In this expression, you can't tell how many zeros or ones there are, how many qubits. So we could use this notation with the tensor product. So 0 with this tensor n up here just tells you that you have an n qubit space and all of the qubits are in the 0 state. So let's make the 3 qubit GHZ state. So how would you do this? Well, to make the 2 qubit GHZ state, which is phi plus, we needed a Hadamard to create superposition and a C0 to entangle the qubits. So these same elements should definitely appear here. So try it for yourself first. Okay, so let's try making our 3 qubit GHZ state. First, we want to create superposition. So let's apply a Hadamard gate on qubit 0. And then we want to entangle our qubits. So we need a controlled knot. And let's do one controlled on 0, targeting 1. Let's see where we're at after we just did this part. So here we have our Hadamard and then our controlled knot. And we can see that we have the state 0, 0, 0 plus 0, 1, 1. So this is almost what we want. but we need to flip the state of this 0 state here, or this is the 0 on qubit 2. And we can do that with another controlled knot. So let's apply another controlled knot, controlled on qubit 1, targeting qubit 2. And now we have our 3-qubit GHZ state that we wanted. So now try making a 4-qubit GHZ state, and then if you want, here's some challenge problems trying to make the following states on your own. So these are some various states. You need to apply similar techniques as creating the GHZ state, but you may also need X or Z gates. Okay, so now we have all the tools we need to talk about quantum teleportation. The name is a little bit misleading because we're not actually teleporting anything physical, we're just teleporting a quantum state. So maybe a more accurate name would be quantum information teleportation. So here's the premise. We have our two good friends, Alice and Bob. Alice has some quantum state psi that she wants to send to Bob. And Bob has some qubit that is going to receive that quantum information. And then after the quantum teleportation scheme, we want Bob to have the state psi. How are they going to do this? They need to use entanglement, and they're going to do this by sharing a Bell pair. So the setup is Alice is going to have a qubit, which is the state psi, which we can say is alpha 0 plus beta 1. And then they're going to share a Bell pair in the state phi plus. So Alice has one half of it and Bob has the other. And remember that the Bell states form a complete basis for all 2-qubit states. And Alice has 2 qubits. So there's nothing stopping her from performing a Bell measurement. And that's exactly what she's going to do. And we're going to see mathematically why this works. So consider the state of the whole system. So we have Alice's state psi here and their Bell pair here. And just to make it a little bit clearer, I'm going to write it out, making it more clear who has what. So a subscript A means that it's Alice's qubit, and a subscript B means that it's Bob's qubit. So we can FOIL this out, and we get this. And now we can think about what these things are actually in terms of the Bell basis. So this here, 0, 0, is actually 1 over root 2 phi plus phi minus. And then 0, 1 is 1 over root 2 psi plus psi minus. Down here we have 1, 0. And this is 1 over root 2 psi plus minus psi minus. And finally, 1, 1 is 1 over root 2 phi plus minus phi minus. Okay, now we can sort this all out and group things by the Bell terms, and we'll get this. Okay, so now we can pretty clearly see that when Alice's state is in one of the Bell basis states, which it has to be in one of them when she measures it, then Bob's state is either the state psi or it's pretty close to the state psi. So for instance, this one here is off by a phase flip on the one state. And this one here is off by a bit flip. And this last one here is off by a phase and a bit flip. So what's going to happen is Alice is going to perform her Bell state measurement, and that's going to cause Bob's state to collapse because the entire wave function is going to collapse. These things are entangled. So let's say, for instance, that Alice measures phi minus, then Bob's state would collapse to be alpha 0 minus beta 1. And the same is true for any of the other three states. So let's summarize these results. So if Alice's result of the Bell state measurement is 0, 0, which is phi plus, then Bob is going to apply nothing to his state because he's already in the state psi. If she measures 0, 1, then he's off by a phase flip. He should apply a Z gate. If she measures 1, 0, then she's off by a bit flip, so she should apply an X gate. So in the last case, if Alice measures 1, 1, then Bob's state is alpha 1 minus beta 0, which is off by a phase flip and a bit flip. So if he first applies an X gate, then that will flip 0 and 1, and then we'll have alpha 0 minus beta 1, and then he will need to also apply a Z gate. So I really want to emphasize here that no information has traveled faster than the speed of light. Bob's state collapsed instantaneously when Alice measured in the Bell basis, but he can't get the state psi until he knows Alice's measurement result, and she can only communicate that to him at the fastest, the speed of light. So now let's look at quantum teleportation in the coding notebook. So remember the steps of the protocol. So Alice and Bob are going to share a Bell pair. And Alice also has a state that she wants to teleport to Bob. Because Alice has 2 qubits, and the Bell states form a complete basis for 2 qubit states, Alice can perform a Bell measurement on those 2 qubits. Then Alice is going to send Bob the results of her measurement over a classical channel. Bob is going to manipulate his state based on Alice's result. And then Bob is going to have the state psi. So you can look at how we would express this protocol as a quantum circuit. So here is Alice's state psi, here is the state 0, and here is Bob's state initialized in 0. Alice and Bob first create a Bell pair, so they entangle their 2 qubits. That's this first Hadamard and C naught. Then Alice is going to perform a Bell state measurement, so she's going to apply a C naught gate and then a Hadamard, and then she's going to measure both of her qubits. So then we have these X and Z gates here, and these double lines indicate that it's controlled on the result of the measurement. So if this bit M0 is 1, Bob should apply an X gate, and if this bit M1 is 1, then Bob should apply a Z gate. So let's try this out. So we're going to have a quantum register with 2 qubits for Alice, a classical register with 2 bits for Alice's measurement result, and then a quantum register with 1 qubit for Bob. So the first thing we're going to do is prepare Alice's state to teleport. So for now, let's just do the 0 state, but we'll change that in a little bit. Then we're going to prepare Alice and Bob's Bell state. So we need to apply a Hadamard gate on Alice's second qubit. And then we're going to apply a controlled knot, controlled on Alice's second qubit, targeting Bob's qubit. Then we want Alice to perform a Bell state measurement. So she's going to do the inverse. So she's going to apply a controlled X, controlled on qubit 0, targeting qubit 1. And then she's going to apply a Hadamard gate on qubit 1. And then finally, Alice needs to measure her qubits. So we're going to measure the quantum register A to the classical register C. Finally, Bob is going to manipulate his state based on Alice's measurement. So he's going to do a controlled X, and this is going to be controlled on Alice's second qubit, targeting Bob's qubit. And then he's going to apply a controlled Z. So this is just a controlled phase gate. It's the exact same thing as a controlled NOT gate, but just controls a phase. and that's going to be Alice's first qubit targeting Bob's qubit. So first, let's just display the circuit. So here we have Alice and Bob entangling our qubits, the H and the X here. And then starting from here, we have Alice doing her Bell state measurement, and she measures her 2 qubits. And then Bob applies an X gate or a Z gate, depending on the results of her measurement. We're going to run this for one shot only, because that's how quantum teleportation would work. So if we run this circuit a bunch of times, Alice's measurement result is going to vary. So she can measure any of the 4 possible outcomes, 0, 0, 0, 1, 1, 1, or 1, 0. I just want to emphasize that Alice's result is changing every time. Now let's look at the protocol with the Bob measuring. So here we're going to have a classical register where we record Bob's result, and then we're going to plot what Bob measures. So in the case where Alice is not doing anything, we should teleport the 0 state to Bob. So let's see if that happens. And now remember the ordering of the bits. So this is going to be the least significant bit, and this is going to be the most significant bit. So Bob's measurement result is actually the leftmost bit. So we can see that over 1,000 times that we did this, Alice's measurement result is randomly 0, 0, 0, 1, 1, 0, or 1, 1, but Bob always measures 0. Now, you may be thinking, okay, well, maybe 0 is just special. You said I could teleport any state. So just as a proof of concept, we could also prepare the 1 state on Alice's qubit. And now Bob always measures 1. And as another proof of concept, let's apply a Hadamard gate to Alice's qubit. Now we know that at this point in the circuit, Alice's qubit is going to be in the plus state. The Hadamard gate rotates 0 to plus. So now, at the end of the circuit here, right before Bob measures, his qubit is going to be in the plus state. If we just measure Bob's qubit, we're not going to learn any information, because he would randomly get 0 or 1. So that's not very good. But remember, we can measure in the X basis if we first apply a Hadamard gate and then measure Bob's qubit. So now we should rotate the plus state back to the 0 state, and Bob should always measure 0. And he does. So now, as a challenge problem, play around with Alice's initial state using all of the gates that we learned from last week. So Alice should prepare some state and then teleport it to Bob. And then Bob needs to do some gates to undo what Alice has done. So I gave as an example here, if Alice prepared the state plus I, that's pointing along the y-axis. Then if Bob applies a S gate, he'll rotate to minus, and then a Hadamard, he'll rotate down to the 1 state, then he should always measure 1. So this is a way to double check that you actually teleported the right state. Today, we learned about entanglement, Bell states, and quantum teleportation. Entanglement is a crucial quantum phenomena for quantum computation. Next week, we're going to learn about circuit composition and control flow, which is going to set the stage for much more complex quantum algorithms. I'll see you then.